Welcome back everyone to part one of our code along of tackling that MNIST dataset with a convolutional neural network. Let's get started. All right, here we are at the notebook. I've gone ahead and imported pretty much the standard imports we did last time, such as torch, torch neural network or NN, torch.nn functional as f, and then a couple of the data loading utilities such as data loader, datasets, transforms, and then make grid from torch vision, as well as numpy, pandas, and some matplotlib and sklearn.metrics. Let's begin by loading up the MNIST dataset. This is actually going to be the exact same way we did it last time. So we'll say transform is equal to transforms, and we'll say to tensor to actually read this in as a tensor. And let's read in our training data as a variable. We'll say datasets MNIST, provide a root. And since I'm located in the same location as the lecture notebook, I'll say dot dot up a directory into data. Since this is my training data, we'll say train is true. We'll go ahead and download it as true, and then say that the transform we want to apply to it is the transform we just created. So transform is equal to transform. Go ahead and run that. And then what we're going to do is the exact same thing, but for the test data. So I'll simply just copy and paste this. I'll change train data to test data. So go ahead and say test data here, datasets MNIST root. Well, what's going to change here is instead of the training is equal to true, we'll say training is equal to false. Go ahead and run that, and now we have our training data and our test data. So if we take a look at train data, we have 60,000 points there, and in our test data, we have 10,000 points. Okay, so when we're working with images, we want relatively small batches. A batch size of 4 is not uncommon, but again, it really depends on factors such as your hardware, and then how large your network actually is. So it's always a little tricky to tell what your batch size to be, or what your batch size should be when you're dealing with new image data. But I would recommend starting small and then working to larger batch sizes. For my case here, I'll go ahead and say a batch size of 10. So let's make 2 loaders. We'll say train loader is equal to data loader, pass in train data, batch size, and I'll choose 10 here. Again, there's kind of no right or wrong value for batch size, something you can experiment with. And we'll shuffle the training data for the training loader. And then for the test loader, same thing, except this case, it's going to be with the test data. We'll also say batch size is 10, and shuffling, we don't need to shuffle for the test, so we'll say shuffle is false. Okay. So coming up next, what we're going to do is define a convolutional model. So what I'm going to first do is essentially break down the convolutional layer and what it's doing. And then we'll put it all together in the next lecture into our actual convolutional network model. So within our model, we're going to have 2 convolutional layers. I'll go ahead and define them right now. And keep in mind, this code that I'm showing right now is just for demonstration purposes. In the next lecture, we'll actually build out the convolutional neural network class. But here, I want to kind of dive a little deeper so the convolutional layers are not as confusing for the first time we see them. So here we have NN, and to call a 2-dimensional convolutional layer, you say conv 2D. And if you do Shift-Tab here, it'll give you the init signature, which is basically telling you what it expects. The input channels, output channels, and then kernel size, which essentially means how big should the filter be, or that image kernel. And notice this will just be defined by one number. So if you say kernel size is 3, then you have a 3 by 3 image kernel. If you say kernel size is 4, then you have a 4 by 4 image kernel. And that's because all image kernels need to be square because of the way the convolution process works out, which is why you only need to give one number for your kernel size. Okay, so in our network, we're going to say the following. We'll say for our first convolutional layer, 1, 6, 3, 1. So let's think about what each of these numbers actually represents. So right now, this first layer has only one input channel. And the reason it only has one input channel is because we're dealing with grayscale images. Later on, we can expand on this for color images. So we have convolutional 2D, it's one grayscale channel. That's our one input channel. Then we'll assign 6 output channels for feature extraction. And these are known as feature maps, essentially the filters that the convolutional neural network will figure out for us. And then since we have 6 of those, the next thing we need to say is, well, how big are each of those? And that's where that kernel size comes into play. So we'll say it's 3, so we have a 3 by 3 filter. And then this last one is the step size to 1. So if you take a look at Shift Tab here again, one more time, and we expand on this, we have essentially our step size or our stride. How big are we going? And then you can also do things like padding. Okay, so right now we have the very basics, and as a reminder, this is the first one is for color channel. It's a grayscale image. Next, I'm going to go ahead and say, make me 6 filters, essentially 6 output channels. So that's another word for the output channels in the convolutional layer. And then we'll make them 3 by 3. That's what that second 3 is for. So that's the actual size of the filter or the image kernel. And then that single output that last one is going to be the stride. So we'll just stride by 1. Okay, so that will be our first convolutional layer. And if you have any questions on that, what does color channel mean, or filters, or kernel size, make sure you take a look at the theory lectures since we went over it there. Next, we're going to have another convolutional layer. So we'll go ahead and say this is nn.conv2d. And this one's going to be 6, 16, 3, and 1. Okay, so why is this second layer going to be with different numbers? Well, this convolutional layer is going to end up taking the results of the first convolutional layer after it's been passed through a pooling function. So eventually, we'll see when we actually build out our network, this convolutional layer, the first one, that takes in the direct image input, is going to be expanded so that it has the 6 filters, and then that's going into some pooling layer, and then that's feeding into convolution layer number 2. So even after the pooling, we're still going to have those 6 filters, although they'll be a little smaller after being pooled. So that's where the first 6 comes from. So this first convolutional layer, we decided kind of arbitrarily that there will be 6 filters. You can definitely play around with the number of filters. Recall, more output channels or more image kernels / filters, the longer the training time will take. So here we have 6. That's where this first 6 comes from. And then 16 is kind of another arbitrary choice. So here, if we start defining this, we have those 6 input filters, and that was from convolution layer number 1. And then we could decide, well, how many filters should convolution layer number 2 expand to? So I'll go ahead and say 16 filters. Again, this is kind of an arbitrary choice. So it's an arbitrary choice for this number of 6 filters and an arbitrary choice for these 16 filters, although hopefully you can experiment with them and see what is an optimal amount of filters. Again, it's really difficult to tell just based off a raw image how many filters you should use. A lot of this is due to experimentation. And next we have to decide, well, what kernel size should we use? And I'll use the same kernel size as before. I'll say these are 3 by 3. And then finally, what is the stride here? And we'll use the same stride as before. It's equal to 1. So these last two numbers, 3 and 1, those are the same as before. It's a 3 by 3 kernel, stride of 1. And then that 6 comes from the fact that we expanded to 6 filters in that first convolutional layer. And this 16 comes from our kind of arbitrary choice that I want to expand it to 16 filters. Okay, so that's our first convolutional layers. Let's go ahead and grab just the very first MNIST record, and we'll do it the exact same way we did it last time. We'll say for I, xtrain, ytrain in enumerate train data, go ahead and then just break. This is exactly what we did for the ANN of MNIST, and this allows us to then just grab that very first batch of data. So if we take a look at the shape of this is one batch of data. So right now, that single xtrain is 1, 28, 28. Now keep in mind, we're calling this off train data, but if we take a look at our train loader is actually designed to feed in batches. So it's going to feed us in 10 images, which means it'll actually be a 4-dimensional array by the time it comes out of train loader. But right now, I just want to deal with a single image to kind of show you what's going on with this train data. So right now I have a single xtrain image. What I'm going to do is I'm going to convert this to be in 4 dimensions, as we previously discussed in MNIST Revisited, so that it better reflects a batch. This is technically just a batch of 1 image. So what I'm going to do here, in order to do that conversion, I will say view this as 1 by 1 by 28 by 28. So that extra 1, that's essentially just adding the dimension of that batch size. Okay, so this is what it looks like. So what I'm going to do is I'll say x is equal to this reshaped or reviewed X train. So then what I'm going to do is I'll perform the first convolution. So I have my single image here. This is just one image. So it's one batch of one color channel image and it's 28 by 28. What I'll do is I'll go ahead and take this guy and I'm going to pass it into that first convolutional layer. And then I'll have an activation function after this. So we pass it through the rectified linear unit. And then what we're going to do is say this is the result of that. So we'll say x is equal to passing in this original x into that convolutional layer through the rectified linear unit as the activation function. And let's go ahead and check the shape of this. So here's what's going on. After you pass in that original single image into the convolution layer, and it's been activated through the rectified linear unit function, we get back this shape of 1 by 6 by 26, 26. So these first two dimensions, that should make sense to us because we have one single image here, and then the 6 filters, well, that's what we asked for up here, 6 filters. Now the question arises is, why do we only have 26 by 26? Wasn't our original image 28 by 28? Well, recall that after you pass over or perform a convolution with this kernel, you may lose information on the borders. And in fact, that's exactly what happened here, because if we take a look at this original conv 2D and expand on this, our padding right now is 0 padding. So because of the size of the kernel and then performing that convolution over the image, we're actually losing a little bit of that border information. So now we end up with these 26 by 26 objects instead of 28 by 28. So keep that in mind. Now, for the MNIST image data set, if you're actually to view the MNIST image data, you'll notice that along the border, it's essentially just no information. Regardless of the number, since they're all drawn very centered onto the images, it's not a big deal to lose that border information, which is why for the MNIST dataset, we decided not to add padding here. However, for real image data, it may be important to actually contain that border information, in which case you'll probably want to add in padding. So that kind of answers the question of why this is now 26 by 26 instead of the original image size of 28 by 28. It's due to the fact that we're losing that border information because we didn't add in padding, as we mentioned in the theory lectures. Okay, so we have one image, those 6 filters, and we have that 26 by 26 shape. All right, the next step is to pass this through a pooling layer. So let's go ahead and call that pooling layer, and we call it off F, and we say f dot max underscore pool 2D. So this is going to perform max pooling in 2 dimensions, and we first put in what we actually want to pass in. So we want to pass in x, the result of that convolutional layer, and then we define that little kernel size, so we'll say 2 by 2, and then we define the stride, so we'll say a stride of 2. And in fact, this is the exact same kernel size and stride choice we made during the theory lecture on pooling layers. And if you have more questions on max underscore pool 2D, what's a little annoying is depending on how you install PyTorch, if you do shift tab here, often it'll just say args and keyword arguments. So when you expand on this, it doesn't really tell you that much information. So what you need to do is essentially Google search this torch.nn maxpool2d. And when you do that, it'll take you to this page, maxpool2d. It'll inform you, hey, here's torch.nn, maxpool2d. And we can see here applies a 2D max pooling, and it was kernel size and stride. Okay, so that's the class it's based off of, but since we're calling it off F, notice that we didn't capitalize M and P. So we go ahead and say the output of that is equal to X. We'll go ahead and run that first pooling layer. And now let's check the shape of this. So the shape of this is now 1, 6, and then 13, 13. So where is this 13, 13 coming from? Well, due to the size of the kernel being a 2 by 2 kernel with a stride of 2, that essentially means you're cutting the size in half. So half of 26 is 13, half of this 26 is 13. So that's how you end up with 13, 13 because of this actual pooling function. So essentially, it's going to be here our first 28 minus 2 for the border because you're losing 1 pixel on each side. So you get 26 divided by 2 because of this pooling, and then you get 13. And so what we're going to do is one last pass through our second convolutional layer and then another pooling pass. So let's go ahead and do that. We'll say x is now equal to f dot rectified linear unit, convolution 2, pass in that x, run that, check the shape of x, and here, same thing, where you just passed it in through that convolutional layer. There's one input, we want 16 filters off of this in that convolutional layer. And then since we lose a pixel on each border side, now we have 11, 11. We'll go ahead and take this guy and pass it in through max pooling. So we'll say max pool 2D, and the same as before. 2 by 2, so a 2 by 2 kernel with a stride of 2. Run that, check our shape, and now we have 1, 16, 5, and 5. So 116, same reason as before. It's one image with those 16 filters from the first convolutional layer. And then 11, well, 11 divided by 2 is 5.5, so what ends up happening is you end up rounding down here. So the final size of 5.5, rounded down to 5, comes from this following equation. We have our 28 by 28 image. We lose a pixel on each border, so that's going to be 28 minus 2. Then we perform one pooling, so that's divided by 2. And then, same as before, we lose another, essentially, set. So we'll say minus 2 there, and then perform one last pooling, so that's divided by 2 again, and you end up getting 5.5. So that's exactly what we did here. Start with a 28 by 28 image. After performing convolution with no padding, you lose that border information, so that's 1 pixel on each side, so that's 26. Then pooling divides it by half, so that's 13. Another convolution, you lose border information, so 13 minus 2 is 11. And then another cut in half through that pooling, 5.5, but ends up getting rounded down to 5, because we can't really round up to make up information, so we have to round down to 5.5. And right after this, what we're going to do is we'll end up feeding this into a fully connected flat layer. So we end up reshaping this to be flat, which is just going to be 1 by 16 times 5 times 5, since that will flatten it out. So we can say x currently, the shape is 116, 5, 5, and if we wanted to feed that to a flattened layer, we'll say view, and then we say -1 because -1 assumes whatever that first batch size is. So we won't really be dealing with just one single image. Instead, we'll be dealing with 10 images. But this allows you to change the batch size as you please. So use a -1 to say, keep that first dimension. And then the second dimension is going to be 16 times 5 times 5. So essentially, whoops, let's go ahead and check the shape of this, since these values won't mean much to us. The last final shape, as we feed into that last fully connected layer, is 1 by 400, which then will feed into a last layer of input, or excuse me, of output of 10. So then it'll go 400 to 10, which is 10, essentially 1 neuron per class. Okay, so if you have any questions on that, I would definitely encourage you to check out our lecture notebook. This is essentially what we're going to be doing in our network. So we did it out step by step. I hope those dimensions, along with the theory lectures, really help kind of drive that point home and have it all make sense. But in case you're stuck, go ahead and open up our lecture notebook, and underneath the define a convolutional model, we actually go and walk through steps by step on all these different calculations. So you have comments here, you have a full explanation of what each step does, etc., for you to check out. Coming up in the next lecture, we'll basically put this all together in an easy-to-use class. Okay, thanks, and I'll see you at the next lecture.